So in this topic, we look at distribution of an error term. And to delve into this, we use the Indian cattle data for the case study example. As always, this is given in more detail back in topic 1, but as a quick summary and recap, this case study is a survey in Bengaluru, a major Indian city which has experienced fast urban growth. One aim of this case study is to investigate the effect of urbanization on dairy production. So in topic 8, we looked at variables that account for variability in the average milk production per cow variable. We ran an analysis of variance, an ANOVA table, and an analysis of deviance table as two different measures of variability, and we got very similar results between them. As a recap on our ANOVA table, we saw that roughly 30% of variability has been accounted for by our variables with this measure of variability, and with our analysis of deviance measure of variability, we saw that roughly 23% of variability in the outcome variable has been accounted for by these variables. So we now kind of dig into a little bit more on ANOVA and analysis of deviance tables and what those kind of differences are. So they're both measures of variability, just the only difference is that an ANOVA can be found from a linear regression model, whereas an analysis of deviance table can be found from fitting a generalized linear model, or a GLM. A linear regression model is a model which can assume a normal distribution, and a GLM kind of assumes a non-normal distribution. In this case, we use a gamma distribution because we saw that the outcome variable was skewed. So we tried that one out. Linear models and generalized linear models measure variability differently. But the results are very similar in terms of what they tell you about the data. Not in terms of what they look like, but about what they tell you about the data. So we're going to throw some p-values in, or calculate p-values, and show them, and see what is significant at this 5% level. So if we have a little look here with our ANOVA table, significant at the 5% level are the variables with a p-value less than 0.05. So just scrolling down, we can see that that's transect, settlement, hours for pasturing, milking technique, all cows pasture, and that's it. Minerals fed is significant at the 10% level because it's less than 0.1, but not at the 5% level because it's still greater than 0.05. So yeah, it's just these 4 variables here are found in our ANOVA table to be significant. In our analysis of deviance table, meanwhile, again, it's the variables with a p-value less than 0.05 are the ones that are significant at the 5% level still. And again, we see that transect, settlement, and hours for pasturing are significant, as well as minerals fed. So we've just put this into a different kind of table here, where we've got our variable, where we've got the p-value in the ANOVA, and we've got the p-value in the analysis of deviance table. And here we see that transect, settlement, and hours pasturing are significant at the 5% level in both measures of variation. However, some variables are only significant in one measure of variation. So milking technique and all cows pasture is only significant in our ANOVA. So when we assume a linear model or a linear distribution for our outcome. Minerals fed is significant in the analysis of deviance table, but not in the ANOVA. So where we've assumed, in this case, a gamma distribution. But what does this mean? Which measure of variation is better for our data? Which one do we listen to here? Well, some variables are significant in only one measure of variation. And this comes down to the error term. the distribution of the error terms tell us a lot about our model. And as we said, with our ANOVA, we've got a linear model, which means that we are assuming a normal distribution. And with our GLM, we assume a non-linear model. And in our case, for the GLM, we fit, because you can say which distribution you want to assume. We've assumed a gamma distribution, which is very skewed. So we'll look at our error of the residuals in the linear model to see how the linear model performs. So in our linear model, we've got here a plot of the fitted values against the residuals. And this looks reasonably randomly scattered. I mean, arguably, is there a small decline happening there? Is there a slight pattern there? Maybe, maybe not. There's no clear pattern present. And this implies that a normal distribution is sensible, and hence that the linear model is a good model to fit. But before we proceed, we can also check a QQ plot. A QQ plot is a plot of your fitted values, against your theoretical quantiles against your standardized residuals. We don't need to go into the specifics of it, but down in the down at the end of this topic is some more information on these different plots and how you can generate them as well. Now, we put in here on the QQ plot this blue line, and basically we kind of, it's fine if there's a little bit of stray at the kind of ends, at the tail ends of the blue line, but here there's a lot of stray in our blue line, in our points, and they don't follow the blue line as much. So this indicates that the distribution of the error term is not normally distributed, and therefore we need to treat the p-values in the linear model ANOVA with caution, because it does not satisfy the normality assumption. And now we can look at we can now actually look at a histogram of our outcome variable. So from the QQ plot, we've kind of seen, okay, a linear model isn't a suitable fit. What we could have done before fitting all of these models and things is to actually look at the data itself and see what the distribution looks like. And we could see then that the distribution of our outcome variable is not normally distributed, and hence this implies that our linear model is not a sensible fit for our data, and instead the generalized linear model with the gamma distribution is probably more sensible and more appropriate for this data. And that is supported by the fact that the linear model is not sensible, is not appropriate for this data, is supported by these error plots. However, it could be that a linear model is completely sensible, but these kind of, when we look at the residuals, we can still see problems in there, and that could be for other reasons, such as that we need to include more variables in our model. We've not accounted for enough variability and the like, which is also dug into in one of the guides at the bottom of this topic. So here the generalized linear model fits this data better than the linear model. What this means is that the p-values in the analysis of deviance table are more representative of the data than those of the ANOVA, because the model fits the data better. So overall, if an error term exhibits a non-normal distribution, a generalized linear model, GLM, might be more appropriate, provided an appropriate distribution is fitted. A GLM is a measure of variability that accommodates error terms which are not normally distributed. If an error term follows a normal distribution, if your outcome variable follows a normal distribution, then a linear model would be a better fit. It's important to note that apart from the error term, these two modeling techniques are interchangeable. They represent two different approaches to measure variability.